So, in the earlier lectures, we had started developing three-dimensional point groups, and today in this lecture we will complete the derivation of all the 32 crystallographic point groups in 3 dimensions. So, starting with first we will consider only the axial crystallographic point groups, where there are no mirrors involved, only rotational axis or roto-inversion axes are involved. And in fact, all of them we have developed, and here is basically a summary of all these axial groups. So, I have divided these axial point groups into different categories. The leftmost column on this table shows directly the point groups that come out of the two-dimensional axial groups, where only one or a single rotational axis is involved, and which are the rotational axes? This is 1, 2, 3, 4 and 6. Next, we started combining the rotational axis, and we had come out with what are the possible valid combinations of these rotational axes. So, the second column on this table, you will notice that these axial groups, they have essentially, we combine 3 rotational axes of the type N22, which was done in the last lecture. Now, so these are the possible combinations. Then here in the last lecture, we had seen 2 more combinations. This was of the type 2, 3, 3, and this is 4, 3, 2 combination, and we also saw that these particular combinations get accommodated in a cube. So, these basically become the cubic point groups. And then finally, I have also included one roto inversion axis only, which is 4 bar, because in the earlier lecture we had seen that roto inversion axes 1 bar, 2 bar, 3 bar and 6 bar, they all, 1 bar is anyway just simple inversion symmetry, while 2 bar, 3 bar and 6 bar can be decomposed into other point groups, and therefore, they are not included in this axial crystallographic groups, but they will pop out later in this lecture. 4 bar, what we had seen in the last lecture, is a unique roto inversion axis which cannot be decomposed into other symmetry operations. So, we have these axial groups in front of us, and you can see that we have a total of 12 axial groups here. Now, to these axial groups we will add the reflection operation and the inversion operation to create other point groups in a very similar fashion as we had done in the two-dimensional point groups before. So, consider, and how do I add the mirror? Well, I have to add the mirror in such a way that I do not add extra symmetry elements which would result in the destruction of the symmetry itself. Now, before I get into the addition part, let me look at some of the names that are there. So, dihedral groups are named, and their symbol that we will use is D, are of the type N22, where N can be 2, 3, 4 or 6, while the other two-fold rotational axes would be perpendicular to this primary rotational axis. These are called as the dihedral groups. The tetrahedral group, the name arises when I put the symmetry inside a cube, just as shown here. I can inscribe a tetrahedron inside this cube like this, and a tetrahedron is a shape which will accommodate the three-fold rotational axis by dropping the axis from each vertex of the tetrahedron onto the opposite base. There are 4 vertices, so we end up with 4 three-fold rotational axes that are present in this cubic point group, while the two-fold rotational axes, as you can see, join the midpoint of pair of edges of the tetrahedron. This also you could see in this figure, and hence to identify such groups, these are called as the tetrahedral group and the symbol used is T. Now, coming to the octahedral group, let us look at how the symmetries is distributed in the cube for 432. Well, 432 we know the threefold, as in the case of tetrahedral group, the three folds are all along the body diagonals, four folds are perpendicular to the cube faces, and the two folds are join the midpoint of the opposite edges of the cube. Now, in this I inscribe an octahedron shape, and this can simply be drawn by joining the midpoints of all the six faces. Now, as in the case of tetrahedron, each face is an equilateral triangle, and there are four faces in the tetrahedron. In the case of octahedron, again the faces are equilateral, and there are 8 faces there. Now, where are the fourfold rotational axes? Well, the fourfold rotational axes are by joining the opposite vertices of the tetrahedron. So, you end up with 3 fourfold rotational axes, and in that similar fashion you can see how the threefold and the twofold rotational axes get accommodated in the tetrahedron. So, for example, the twofold rotational axis is join the midpoints of the opposite edges of the tetrahedron, and you will get the twofold rotational axis. So, that is why this group is called as the octahedral group, and the symbol used is O. And roto-inversion I have already discussed in the last lecture. So, now we are going to add mirrors to these axial groups. Before I add the mirrors, this is just showing the representation of all these axial groups on a stereographic projection. All of them except for 2, which are the 2,3 and 4,3,2, their stereograms. For these stereograms we will come at a later part of this lecture, because in all other cases we always had a axis which is perpendicular to the stereogram, while in the case of 2,3 or 4,3,2 point groups, we also now have axes which are at angle to the plane of the stereogram, and therefore they look slightly more complicated because of the way the arrangement of symmetry is there. Now, I will show you how we are going to add the mirrors to these axial groups. So, these are again I have just listed down all the axial groups here, and the symmetry elements that we are going to add are mirror and inversion. Now, sigma h is a mirror in the horizontal plane. So, here you can see the example of a mirror which is perpendicular to the rotational axis. So, the main primary rotational axis, so in the case of 1, 2, 3, 4 and 6, it is obvious that we can add the mirror perpendicular to it. In the case of 2, 2, 2, we will add a mirror perpendicular to one of the twofold axis. In 3, 2, we will add the mirror perpendicular to the threefold axis, and so on. So, sigma h is called as the horizontal mirror. Similarly, I can add a vertical mirror. In the case of the vertical mirror, it will be containing one of the primary rotational axis, and this is depicted in this fashion. Now, consider the third mirror, the diagonal mirror. The diagonal mirror would be interleaved between two axes in a fashion like this. So, now this is a diagonal mirror where this mirror is essentially bisecting two of the twofold axes, and one of the twofold axes is contained in the mirror. So, it is basically in between this axis and this axis, while it is containing this axis. So, diagonal mirror is basically between two axes. So, then quite clearly we cannot define a diagonal mirror for the point groups 1, 2, 3, 4 and 6, since there is only one axis involved here. And in some cases we may not be able to put a diagonal mirror, because it may end up generating more rotational axes, destroying the symmetry. So, it is important that the mirrors have to be added carefully, so that we do not disturb the rotational axes that are present in the point group. And then lastly, we add an inversion center, as you can see in this figure. So, there is not much explanation required here. So, now let us start developing the 32 crystallographic point groups, out of which we have already developed or at least shown 12 of them, and now we are going to develop the remaining crystallographic point groups. So, the top row in this table shows the first 3 axial groups, group 1, group 2, group 3, and along with the Schoenflies notation C1, C2 and C3. Now, to this I have added in the second row a horizontal mirror. So, let us consider this particular point group to which I have added a horizontal mirror. Well, in this case anyway there was no rotational axis, there was in fact no symmetry to begin with. Now, basically I have added a symmetry, and as a result the stereogram shows a blue filled circle and a red open circle. Now, just to get this legend right, the blue color indicates whether the point is in the upper hemisphere of the sphere from which we get the stereographic projection, and the open circle shows the point is below the projection plane or the equatorial plane, as was discussed earlier. The red color indicates is left handed, the blue color indicates that the point is right handed. Now, with this out of the way, you can now clearly see, because the mirror is added in the horizontal plane, the blue dot which is in the upper hemisphere gets reflected down. So, from up a point is generated down, which is shown as a red open circle. Why red? Because of the reflection operation the handedness changes. Now, consider adding a horizontal mirror the point group 2. Well, in this case we had 2 points in the upper hemisphere. Those 2 points get reflected down through the mirror, and as a result we get our motifs in this fashion. Now, on the right, so one is I have drawn one figure with the motif, and the figure next to it shows the symmetry. So, for example, here the symmetry that is indicated, there is a two-fold rotational axis in the center, and there is a circumference of the stereogram is now shown as a bold black line to indicate that this is a mirror. Within the two-fold rotational symmetry, you can notice a white dot. It is basically a small circle to indicate that there is inversion as well. Now, the notation for the point group. The notation for the point group is 2 upon m, basically saying that the mirror is perpendicular to the two-fold axis. In the Schoenflies notation, we simply say that we have added a horizontal mirror to the cyclic group C2. Now, coming to adding the mirror to the threefold. So, added a horizontal mirror, which means the mirror is again perpendicular to the threefold, and basically the projection plane is the mirror itself, shown by the bold black line. Now, what happens is that the 3 up dots get reflected down, the handedness changes, and this is how we have already seen this group when we are discussing roto inversion symmetry as the 6 bar, which can be decomposed into a threefold rotation and a mirror. And you can likewise see the Schoenflies notation, the H is added to C3. Now, if I add a vertical mirror now, so adding a vertical mirror, let us say I add it to the point group 1. Well, what does it mean? If I add a vertical mirror, basically I have added a mirror like this, and as a result the up point is reflected to the left and the handedness changes. This essentially is the same point group as the point group M. It is just a question of perspective, the way one looks at it. Add a vertical mirror now to the two-fold or for the point group 2. When I add a vertical mirror to the point group 2, essentially the two-fold will lie now within the mirror, and we have already seen that if I have a two-fold and a mirror intersecting it, mirror containing it, then automatically a mirror will get generated 90 degrees to it. This we have seen while we are discussing the two-dimensional point groups, and you can figure out that all the points are up except that their handedness is changing as a result of this vertical mirror. So, point group notation is 2 mm, just the same as the 2 mm notation in the two-dimensional point group, and C2V is the Schoenflies notation indicating that a vertical mirror has been added. Similarly, I can add a vertical mirror to the three-fold, and I will leave this to you to understand. It is very clear from the diagram how this is working. Diagonal mirror is undefined for all the groups which have only one rotational axis. So, there is nothing to be done here. Add a inversion center to point group 1. Well, you simply have a inversion center here indicated by a small circle, and that is the only symmetry that is there, and basically the up point gets inverted to the down point along with the change in handedness. If I add an inversion center to the point group 2, essentially I will get the same group as already discussed called the 2 by m point group, and you can see why that would be the case, because if I add an inversion, essentially I will end up generating the same point groups. Now coming to adding the inversion center to the three-fold rotational axis, this is nothing but basically becomes a three-fold roto inversion axis out here, and this also we have seen in the last lecture. Similarly, I can add horizontal mirror to the four-fold rotational and I will get the stereograms as shown. I can add horizontal mirror to the six-fold and I will get the stereograms which are quite easy to interpret. Now coming to the 2 to 2 point group, and I add a horizontal mirror, essentially when I add a horizontal, it is going to be perpendicular to one of the two folds, and the stereogram, you can see how the stereogram will change because of the horizontal mirror, and this point group essentially it is going to generate two more mirrors, one mirror perpendicular to the horizontal mirror, in fact and the third mirror which would be in the equatorial plane. So, all these mirrors will be perpendicular to each other and each of these mirrors will be containing the two-fold rotational axis, and this is basically called 2 by m, 2 by m, 2 by m, because each mirror, there is a mirror perpendicular to each of the two-fold axes. The Schoenflies notation is called D2H. Essentially, this is now comes under the category of dihedral group. So, 2 to 2 is simply referred to as the D2 group, which is out here, and H is added to it to show that a horizontal mirror has been added. Then one can add now vertical mirrors to the point group 4. Well, that mirror is going to contain the four-fold axis, and if you recall, you will end up getting a mirror perpendicular to it and you will get mirrors bisecting the angle between these two perpendicular mirrors. So, there would basically be mirrors at 45 degrees to it, Schoenflies notation C4V, and this point group is simply called 4 mm. In fact, it is just an extension of the two-dimensional plane group. Now, I think six-fold, adding vertical mirror to six-fold, this is again a group that we have got directly by extending the 6 mm point group in 2 dimensions. So, this I think should be clear. Now, if I add a vertical mirror to the case of 2 to 2, basically now that vertical mirror will also be containing two-fold axis, hence two more mirrors will get generated and this point group would be the same as this one. So, we do not list it here. Now, diagonal mirror, well, undefined for the case of point group 4 and 6, but we can put a diagonal mirror in the case of the point group 2 to 2, and this is my diagonal mirror that is added, and because of the twofold, this perpendicular mirror gets generated. If I add a diagonal mirror here, then this point will get reflected with the handedness changed, and in this fashion you will get a stereogram like this, because there is another mirror here. So, there will be, and now what is this point group? So, first of all, to note that this axis is the 4-bar, 4-fold rotational axis and a 4-fold roto-inversion axis, and we have already seen that the subset of the 4-fold roto-inversion axis is a 2-fold axis indicated by the ellipse, dark ellipse within the square. And the international notation is simply, we list down the independent symmetry. So, 4-bar 2m, Schoenflies dihedral group D2 add D. Now, these are, by adding inversion center, we do not create any new groups. So, we can move to the next. So, the next dihedral group is the point group 3,2. Now, this point group 3,2, adding a horizontal mirror, we get basically the mirror will be perpendicular to it, some more mirrors get generated, and of course, we have international notations is 3 upon m, m2. Moving to the next 4,2,2, I think I will leave this to you to analyze. The next one 6,2,2, I will leave this one also for you to analyze. So, the groups horizontal mirror added to D4, horizontal mirror added to D6, you try to analyze yourself. Then again nothing new gets generated when I add vertical mirrors to the top 3 axial point groups. We can move on to diagonal mirror here also. So, here what we are doing, basically we are adding a diagonal mirror in between two fold, and this 3-fold will rotate these diagonal mirrors by 120 degrees, generating 2 more mirrors, and then the stereogram with the motifs can be produced by taking the 3,2 point group, add the diagonal mirrors here, and then reflect them to get some more motifs with change in handedness. If I add a diagonal mirror to 4,2,2, very interesting, we get a point group 8-bar 2m. 8-bar means 8-fold roto-inversion axis. So, 8-bar is a non-crystallographic axis, and hence we are not interested in such groups. Same thing happens if I add diagonal mirror to 6,2,2, I get a 12-fold roto-inversion axis, not a crystallographic axis. Now, inversion center produces nothing new. So, we move on to the next set. Here we have now the cubic point groups, but before that we have already seen the 4-bar or the 4-fold roto-inversion axis, and in Schoenflies notation this is called S4. Now, here we had seen this in the last lecture, so I do not need to cover. Now, come to, and then if I add other things to it like the horizontal mirror, vertical mirror, diagonal mirror I cannot add because there is only one axis of diagonal mirror, one 4-bar axis. So, diagonal mirror is undefined, but adding horizontal, vertical and inversion just produces the point groups that we have already seen. Now, coming to the tetrahedral point groups. So, let us come to 2,3. Let us look at a bigger version of this. So, this is a stereogram where now the 3-fold, as you know, we have already seen that they are essentially running along the body diagonals of the cube, and they are at angles which are not 90 degrees, and they show up on the stereogram like this. So, when we do a projection from the sphere, so the rotational axis drawn from the center of the sphere, and where it intersects the surface of the sphere, that point gets projected so as the 3-fold rotational axis. And as you can see, there should be 4 3-fold axis, that is sure. In the 2,3 group, 2-fold rotational axis is perpendicular to the cube faces. So, they show up in the center and at the peripheries, and as you can see, there are 3 2-fold axes. One is running horizontally, the other one is vertically, and the third one is in the center perpendicular to this figure. So, all the 3 2-fold rotational axes are perpendicular to each other. And since there are only pure axial group, from the motifs you can see there is no change in handedness at all. Now, coming to adding a horizontal mirror to the 2,3 point group. So, if I add a horizontal mirror, So I am adding a mirror in the projection plane or the equatorial plane of the sphere, and it is very straightforward group. Just take all the motifs which are up, they go down, and the handedness changes, as you can see in this figure. The two-fold rotational axes remain where they are. The three-folds also remain, but this is interesting that these three-fold, you can see a open circle inside it to indicate that this is a three-fold roto axis. The group is simply called 2 upon m, two-fold is perpendicular to the mirror, and 3 bar the roto inversion axis. So this is also, I think, pretty straightforward. Then let us look at the TD, which is basically I am adding a diagonal mirror to the 2-3 point group. Now I have not explained what is T. So this is a Schoenflies notation. So since this is a tetrahedral group, it starts with T. Let us look at this adding a diagonal mirror to the point group 2-3. So essentially this is my diagonal mirror, and out here this is a four-fold roto inversion axis, and the three folds are at the same locations, and you can see this there are 3 four-fold roto inversion axis. So one is perpendicular to this figure, one is running horizontally, the other is running vertically, and they are at 90 degrees to each other, and the international notation for this point group is 4 bar 3m. Schoenflies is TD, adding a diagonal mirror to the tetrahedral group. Now we are only left with 2 more point groups, the octahedral axial group and a horizontal mirror added to it. So the octahedral axial group, enlarged version, basically we have combined 4-fold, 3-fold and 2-fold axis. Now you can see from the stereographic projection the various angular relationships, and in this also no change in the handedness takes place because this is a pure axial group. Now to this group, let us add a horizontal mirror. So when I add the horizontal mirror, this group would be Schoenflies, it will be called as OH, octahedral group, horizontal mirror added. The international notation is basically mirror perpendicular to the 4-fold axis, and we will see this in a bigger diagram. So I have added a horizontal mirror, but as a result I get many more mirrors. So because of the other rotational axis, so I get basically I have added horizontal mirror, which is this one. Then I get some more mirrors. So this is let me call this as, this is the mirror that we have added, and the new mirrors are this one, I get this one, and you also see these are also mirrors, but these mirrors are at an angle because of the complex operation of these 2-folds, 3-fold axes. So, and in fact basically this curved line that you see basically are grid circles. So essentially you are seeing a mirror plane getting projected onto the stereographic projection. So one running at a certain angle and the other one is out here. So this is the other one which is running at a different orientation, and then along with the operation of all these reflection operations, we get this pattern in this fashion, and I have already explained the notation for this. Now let us just come back to it. If I add a vertical mirror to 4-3-2, essentially I am producing the same point group like when I added a horizontal mirror, for the simple reason that when I added a horizontal mirror, the vertical mirror also got added. Now what about diagonal mirror? Okay, 4-3-2, let us look at 4-3-2 again. Where do I add the diagonal mirror? If I try to add the diagonal mirror, so if this is, let us say, a diagonal mirror, then 2-fold will get reflected onto the 4-fold and the 4-fold will get reflected onto the 2-fold, we will end up destroying the symmetry. So This is not possible, not allowed, I should say. So that is the reason why we cannot have a point group generated when I added a diagonal mirror. Inversion center, if I add, again I get the same group as the octahedral group with the horizontal mirror added. So in fact, we have now completed the discussion, and these were all the 32 possible point groups in 3 dimensions. In the subsequent lectures, we will look at the 3-dimensional Bravais lattices, how they are evolved from symmetry, and then we will basically add the symmetry elements to those to get a few, only a few space groups in 3 dimensions. Thank you.